The moment, everything changes. A sealed clay vessel rests beneath layers of dry earth. It has been untouched for centuries. No sunlight, no airflow, no human interference. Just silence, pressure, and time. When archaeologists finally uncover it, the contents seem unremarkable at first glance. Small, shriveled seeds. Lifeless, or so it appears. But then something unexpected happens. Those seeds are placed into soil. Water touches them for the first time in hundreds of years. Days pass. Then something extraordinary begins. Tiny green shoots push upward, breaking through the surface. Life returns. This is not speculation or folklore. It is documented reality. Seeds preserved underground by Native American communities have been found capable of sprouting after centuries, sometimes even after more than 1,000 years. How did this work so well without modern technology? Not just storage. A system at first glance, it's easy to imagine ancient seed storage as simple. Maybe baskets tucked away in cool areas. Maybe clay pots placed in shade. But that assumption falls apart almost immediately. What existed instead was something far more advanced. These storage systems were carefully designed environments. Every detail mattered. Temperature, moisture, airflow, even protection from insects and light were all controlled with surprising precision. This wasn't accidental. It wasn't guesswork. It was environmental engineering. Communities understood that seeds are not inert objects. They are living systems in a dormant state. Treat them incorrectly, and they decay. Treat them properly, and they can survive for generations. So the goal wasn't just to store seeds. The goal was to preserve life itself, underground, nature's perfect storage chamber. The real secret begins with location. Instead of storing seeds above ground where temperatures swing wildly between day and night, many native communities place them underground, not randomly, but with intention. The earth acts as a natural insulator. During hot summers, the soil remains cool. During freezing winters, it stays relatively stable and above extreme cold. This creates a consistent temperature zone that protects seeds from stress and degradation. Above-ground storage might fluctuate by dozens of degrees within a single day. Underground, those fluctuations are dramatically reduced, and stability is everything. Seeds exposed to constant temperature changes begin to break down internally. Their biological structures weaken, viability drops. But in these underground pits, that process slowed down to a near standstill. The seeds weren't dying, they were waiting. Depth was never random. The depth of these pits wasn't chosen casually. Too shallow and frost could penetrate during winter. Too deep and moisture levels might increase or oxygen could become too limited. Communities learned through generations exactly how deep to dig. They found that perfect middle ground, a depth that avoided freezing temperatures but also escaped the intense surface heat, a depth that balanced airflow and dryness. This level of precision didn't come from instruments or sensors. It came from observation, repetition, and shared knowledge passed down across generations. Moisture, the silent destroyer. If temperature was one challenge, moisture was another. Too much moisture invites mold, bacteria, and decay. Seeds can begin to rot or even start germinating prematurely. But too little moisture isn't safe either. Excessive dryness can damage the internal structure of the seed. So balance was critical, and this is where the design of containers becomes fascinating. Clay vessels were often used, but not just any clay pots. These were crafted with specific properties. The porosity of the clay allowed for minimal air exchange, not enough to let moisture flood in, but just enough to prevent stagnant air from building up. Some containers were lined with ash. Others used adobe-like coatings. These materials absorbed excess moisture while maintaining a dry interior environment. It's the kind of balance modern laboratories try to achieve with machines and sensors. Here it was achieved with earth, clay, and experience. Airflow, the invisible factor. Air might seem harmless, but oxygen plays a major role in seed degradation. Too much oxygen leads to oxidation, slowly breaking down the seed over time. Too little oxygen, however, can trap moisture and create harmful conditions. So again, balance. Many storage vessels were sealed, but not completely airtight. Natural resins, tightly fitted lids, and layered materials reduced airflow without eliminating it entirely. This subtle control allowed seeds to remain dormant without suffocating or degrading. It's a level of nuance that reveals just how deeply these systems were understood. Darkness was essential. Light is another factor that often gets overlooked. Exposure to light can trigger biological processes in seeds, shortening their lifespan. It can also increase temperature and promote unwanted chemical reactions. That's why these storage pits were buried deep enough to eliminate light entirely. Complete darkness, no interruptions, no cycles, just a stable environment where seeds could remain in suspended animation. Protection against pests. Insects and rodents pose a serious threat to stored seeds. Even a small infestation can destroy an entire cache. But these systems accounted for that too. Certain plant fibers and aromatic herbs were placed alongside seeds. These natural materials acted as deterrents, keeping insects away without the need for chemicals. Some coatings and linings also discouraged pests while maintaining the integrity of the seeds. It was an early form of biological pest control, developed through careful observation and experimentation, a strategy built for survival. All of these elements come together to form something much larger than storage. This was a survival system. These communities weren't just preparing for the next harvest. They were planning for droughts, floods, failed seasons, and long-term uncertainty. Seeds were stored not just for a year, but for decades, sometimes longer. This meant that even if crops failed for multiple seasons, there was still a reserve, a backup, a way to start again. That kind of thinking transforms agriculture into resilience. Diversity was the real insurance. Another key element often overlooked is variety. Instead of relying on a single crop, multiple seed types were stored together. Different strains, each adapted to different conditions. Some handled drought better. Others thrived in cooler temperatures. Some could grow in poor soil. By preserving this diversity, communities ensured that no matter what conditions came next, at least one type of seed would succeed. This approach is now considered a cornerstone of climate resilience, but it was already in practice centuries ago. Seeds as living archives. A seed isn't just a future plant, it's a compact package of genetic information. Inside each seed is a record of adaptation, traits that have been selected over years of observation and cultivation. By preserving seeds, these communities were preserving knowledge. Not written knowledge, but biological knowledge. Traits that made crops stronger, more resilient, more suited to specific environments. Every seed stored underground carried that legacy forward. Continuous learning through generations. These systems didn't appear overnight. They were refined over time. Each planting season provided feedback. Which seeds performed best? Which resisted disease? Which survived harsh conditions? The best seeds were selected and stored again. Year after year, traits improved. Crops became more aligned with their environment. This created a cycle of continuous improvement. And the knowledge wasn't held by a single person. It was shared across the community. Elders taught younger generations how to identify the best seeds, how to prepare storage pits, how to manage moisture and timing. It was a living system of knowledge, constantly evolving. Storage as a communal responsibility seed. Preservation wasn't treated as a simple task, it was a responsibility. In many communities, specific individuals or families were entrusted with managing seed storage. They monitored conditions, checked for damage, rotated supplies, and ensured everything remained viable. This role required attention to detail and deep understanding, and it was respected. Because the survival of the community depended on it. The deeper this system is examined, the clearer it becomes that this wasn't just practical knowledge. It was a sophisticated understanding of biology, environment, and long-term planning. And in many ways, modern science is still catching up. In Part 2, the focus shifts to how these ancient methods align with modern seed science, how archaeologists and biologists are rediscovering their effectiveness, and why these underground systems might hold the key to future food security. When ancient practice meets modern science. As more seed caches are uncovered, something unexpected happens in laboratories. Researchers don't just study these seeds, they test them. And when those seeds germinate, when life emerges from something buried for centuries, it forces a shift in perspective. These aren't just historical artifacts. They are functioning biological systems that have survived extreme spans of time. That kind of survival isn't luck, it's design. Modern seed banks rely on carefully controlled environments, low humidity, stable temperatures, minimal light, and reduced oxygen levels. These are considered essential for long-term preservation. And yet, when ancient storage systems are examined closely, those exact same conditions appear again, achieved without electricity, without digital monitoring, without synthetic materials, just clay, soil, plant fibers, and experience. The science inside a seed. To understand why these systems worked so well, it helps to look at what a seed actually is. A seed may appear dry and lifeless, but inside it is a highly complex structure. There's an embryo, enzymes, stored nutrients, and protective layers. Everything needed to grow a new plant is already there, but all of it is incredibly sensitive. Too much moisture can activate enzymes too early or cause mold. Too little moisture can damage internal tissues. Temperature swings can stress the cells. Oxygen can slowly break down internal compounds. So for a seed to survive decades or even centuries, all of these variables have to stay within a very narrow range, and that's exactly what these underground systems achieved. Slowing time itself. One of the most important effects of these storage pits was the slowing of biological processes. Inside a seed, even in dormancy, there is still activity. Very slow metabolic processes continue over time. These processes gradually consume energy and degrade the seed. But when temperature is lowered and stabilized, and when moisture and oxygen are controlled, those processes slow dramatically. Not stopped, just slowed. This is what allowed seeds to remain viable for so long. They weren't frozen in time, but they were preserved in a state where change happened so slowly that centuries could pass without complete degradation. Clay vessels. More than containers. Take a closer look at the containers themselves, and their importance becomes even clearer. Clay wasn't chosen just because it was available, it was chosen because of how it behaves. Clay is slightly porous. That means it allows tiny amounts of air exchange. Not enough to disrupt the environment, but enough to prevent harmful buildup of gases or moisture. When fired at certain temperatures, clay also becomes resistant to water and pests. Its surface can be smoothed or burnished to further control how much air and moisture pass through. Some vessels even show signs of ash linings, which absorb humidity and help maintain a dry interior. This turns a simple container into a controlled microenvironment. The role of woven materials. Before seeds were sealed away for long-term storage, they often went through a preparation phase. Woven baskets made from grasses or fibers played a role here. These allowed seeds to dry evenly while still being protected from sunlight. This step was critical. Seeds that are stored with too much internal moisture are far more likely to fail. Proper drying ensured that once seeds were placed into sealed environments, they were already in a stable condition. Again, this reflects a deep understanding of the entire preservation process, not just the storage phase. Engineered pits, not simple holes. The pits themselves were carefully constructed. Walls were often reinforced with clay or compacted sediment. This created a barrier against external moisture while still allowing controlled airflow. Sometimes layers of sand or plant fibers were added to further regulate humidity. Everything about these pits was intentional. They weren't just digging holes and hoping for the best. They were building environments. Rotation and maintenance. Another detail that stands out is how these storage systems were maintained. Seeds weren't simply stored and forgotten. They were rotated. Older seeds were used first. Newer seeds replaced them. This ensured that the overall collection remained viable over time. This kind of rotation is a principle still used in modern seed banks and food storage systems. It shows an understanding that preservation is not a one-time act. It's an ongoing process. Knowledge without written records. What makes all of this even more remarkable is how the knowledge was preserved. There were no written manuals, no scientific journals, no digital databases. Instead, knowledge was passed through action. Younger members of the community learned by participating. They observed how seeds were selected, how pits were constructed, how vessels were sealed. They learned timing, when to open a cache, when to reseal it, how to recognize signs of damage or contamination. This created a continuous chain of knowledge, stretching across generations. Archaeology meets biology. When archaeologists uncover these storage systems, they often collaborate with biologists to analyze what they've found. And again, the results are consistent. The internal conditions of these ancient caches match the requirements identified by modern science for long-term seed viability. Low humidity, stable temperature, minimal light, controlled oxygen, protection from pests. Every major factor aligns. It's not just similar, it's almost identical in principle. Lessons for today. Fast forward to the present, and agriculture faces new challenges. Climate instability, soil degradation, loss of crop diversity. Modern farming often prioritizes uniformity. Large-scale production of a few high-yield varieties. While efficient, this approach comes with risk. If conditions change suddenly, those uniform crops may not survive. Ancient systems approach this differently. They prioritize diversity, resilience, long-term planning, and those priorities are becoming increasingly relevant again. The return of ancient methods. In many regions, traditional seed preservation practices are being revived. Indigenous communities are reintroducing crop varieties that were nearly lost. Corn, beans, squash, and other staples are being grown again, using knowledge that has been preserved for generations. These efforts are not about recreating the past. They are about solving present-day problems. Because the challenges being faced today are not entirely new. They are variations of challenges that have existed before. And solutions already exist. Blending old and new modern science doesn't have to replace ancient methods. In many cases, it can learn from them. Subterranean storage offers low-energy alternatives to refrigeration. Clay-based materials inspire new approaches to moisture regulation. Crop diversity strategies inform modern breeding programs. It's not about choosing one over the other. It's about combining them. A blueprint for resilience. When viewed as a whole, these seed storage systems form something powerful. A blueprint, a system built on understanding, observation, and long-term thinking. It accounts for environmental variability. It protects genetic diversity. It ensures continuity across generations. And most importantly, it works. Because it already has. Why this still matters. The image of a seed lying dormant underground for centuries, only to sprout again, carries a deeper meaning. It represents resilience. It shows that with the right conditions, life can endure far longer than expected. And it reminds us that some of the most effective solutions are not always the newest ones. Sometimes they've been there all along, waiting to be rediscovered. Native seed storage pits were never just about keeping food safe. They were about securing the future. Through careful control of temperature, moisture, air, light, and pests, these systems created environments where seeds could remain alive for decades, even centuries. They combined environmental awareness, material science, and long-term planning into a single, cohesive strategy. And today, as global food systems face increasing pressure, those same principles are becoming relevant once again, not as relics of the past, but as tools for the future. If this kind of hidden knowledge and ancient innovation sparks curiosity, make sure to subscribe for more content that uncovers the science behind historical systems that still shape the world today. There's always more beneath the surface, and sometimes the answers to tomorrow's challenges are already buried in the past.